do it. Alrighty. So guys, I have not graded your tests yet. I am going to do that this afternoon. So hopefully they'll be in Power School by the end of the day. I haven't graded any of them. I haven't even looked at them. That's how invested I am. All right, let's have at it here. So it is, in a way, I think it's great. We have two units left, guys, of the year. That's it, 2. We have energy, and then we have our space unit. Space, where most of you preside during this class anyway. So we are getting into energy. The nice thing about energy is the formulas that we're going to learn within energy, they are not difficult math formulas. All right? And most of them are derived from previous formulas that we've already learned. So energy, generally speaking, tends to be, I'm going to say, one of the easier units. A, because of the math formulas are simple, and B, because of the project that we do. So on Thursday, we are going to start our initial research phase of the Rube Goldberg machine. So you're going to understand why we're doing Rube Goldberg machines by the time class is over today. So energy. That's what we're doing. All right. It says energy cannot be created or destroyed. So here it is, guys. Yet another conservation theory within science. I should say another law, not theory. This is straight up truth. So energy cannot be created or destroyed. It may be transformed from one form of energy into another, but the total amount of energy never changes. All right. So we just got done talking about the conservation of momentum, where the total momentum before a collision within a system is the same as the total momentum after within a collision. So it doesn't change. Energy is very similar to that, guys. Energy does not change. We know that energy changes forms. There are all sorts of examples that you guys see every single day of energy changing forms. All right? So, very basic example. You go home, your phone is dying. You plug your phone into the wall. What happens to your phone then? Yeah, it charges, but as soon as you plug it into the wall, what happens to the screen on your phone? It'll light up. All right? That is energy conversion. That is electrical energy into light energy. All right? Right now, you sitting there, just sitting there breathing and living, you are doing energy conversion. How so? Does anyone know how you're showing energy, conservation of energy? We need oxygen to breathe, correct. What does oxygen help do within our cells? Oh, I love it, cellular respiration, which the end product, guys, of cellular respiration is energy. Okay? You need to eat, you need oxygen to break down the food that you eat within your cells, that in return, you get all sorts of energy, mechanical energy, energy of movement. Like I said, though, even if you're just sitting there doing nothing, what type of energy are you giving off then? Heat. Yeah, great. Thermal energy. All right? So, energy is not created or destroyed. It simply changes forms. Now, here's the question. If it's not created or destroyed, where did all the energy come from? Where did all this energy that we have come from? It had to have been created at one point in time. Let me put that out there. What's that? The ground? We're getting closer. Yep, all the energy that we use on Earth comes from the sun. But think even further back. How was the sun created? How was exactly the Big Bang? All right? So we will learn more about the Big Bang when we get to our space unit, but all the energy created within our universe, guys, has been in our universe since the moment of the Big Bang. Yes? It is not, though, because the energy in the chemical composition, you will decompose back into the ground. Then that energy, depending on how we're used for energy as far as fertilizer goes, as far as our body will be recycled, and all that energy that we have will be used somewhere else. All right? This is the whole theory, guys, behind ghosts. All right? What if you get cremated? Well, the energy that you still have, whether it's thermal energy, it's still, if you get cremated, you're getting burned, which is creating thermal energy. Okay? Now, don't get confused with all the energy is then going to be technically reused for a real purpose. All right? Because if you slide a book across the table, that book is going to create energy. It's going to create thermal energy through friction, but we're not using that energy. All right? Just understand that it's just simply changes forms. Okay? All right, so what is energy? Technically, it's the ability to do work. That is the definition of energy. If you can do work, which we are going to talk about what work is later on, if something does work, it is using energy. So the combination of energy and matter make up the universe. So matter is substance, and energy is the mover of the substance. So our entire universe, guys, consists of energy and matter. All right? Now, there is energy all around you. The only time you can feel or you know about energy is when it does change forms. Okay? So, for instance, we can talk about thermal energy. When can you feel thermal energy? Sure. Yep. What if I were to turn the air conditioning on here? Would you feel thermal energy then? Yeah, because it would be a change within that thermal energy. All right? So, I put up here, it says we sense energy only when the score changes, so either a transformation from one form of energy to another or a transfer of energy from one point to another. That is when we know energy is around us. So these are the two big categories, guys, we're going to deal with specifically today, potential and kinetic energy. I got a feeling that some of you already know what the difference between potential and kinetic energy is. Anyone want to be the brave soul and let me know what that difference is? Let's look at the words then. Potential. What does it mean to have potential? Yeah, you got it in you, right? It's possible. So, therefore, if I'm going to stand up here and hold this rocket in front of you, you wouldn't necessarily think there's a lot of energy there. But guess what, guys? There is energy there. It's called potential energy. It has the potential to exhibit energy. What do I have to do in order to have this have energy? Let it go. All right? So that potential energy, as soon as I let it go, will switch into kinetic energy. Okay? So therefore, potential and kinetic energy are the big, broad categories of energy types. Kinetic energy is the energy of motion. All right? So once an object gets set in motion, it's considered kinetic energy. Potential energy is considered the energy of potential, or possible energy. All right? Or energy of position. So the higher I would hold that rocket, the more potential energy it has. Because we know that when we drop an object, as it falls, it accelerates at 9.8 meters per second squared. All right? So the higher up I have it, the more energy, the more potential energy it has. So, potential energy. Many different types of potential energy. There's gravitational potential energy, elastic potential energy, chemical potential energy. Which did that rocket when I was just holding an exhibit? Which of these three? Gravitational potential energy. Exactly, because gravity is what's going to create the energy as far as pulling it down to Earth. Good. So any questions on the two broad categories, kinetic and potential energy? All right, let's move on then. So here's what I just said before. So potential energy is the energy of position or energy in storage. It's got the potential to exhibit energy. It's just waiting to be released. All right? So water behind a dam, hammer over your head, food on the plate. How is food on the plate? How does that have potential energy? Yeah, exactly. Because food, well, sure, it could slide off, I guess, if you're going to pick it up. Sure. But Jenna said, because it's going to give you energy. Yeah. When you eat food, guys, you eat food for the energy. All right? So once you eat it and your body starts to digest it through cellular respiration, it's going to convert that energy from potential energy into a whole different slew of energies that your body's going to use. Okay? And kinetic energy is the energy of motion, so the form capable of actually doing work. So the flow of the water, the falling of the hammer if I were to drop it, and electrons generating ATP within a biological cell. I love being able to work bio back into physics. You guys are like, I hate it. All right, here we go. Formulas. Like I said, these formulas, guys, are not difficult. It's simply multiplication and division. So if we're trying to figure out the potential energy of an object, we need to know three things about that object. We need to know mass. We know what G is. What's G always? Gravity, 9.8. If you want to use 10, go ahead and knock yourself out. H, height. Okay? Mass times gravity times height is going to give you the potential energy within this. Now, one thing I did not put on here is the unit of measurement for these. Depending on which way it's going up or down. So if it's going up, it's going to be negative 9.8. If it's going down, it's going to be 9.8. It is not. Here's the deal. Energy, guys, all energy, regardless of what type of energy it is, it's going to be a joule. Okay? So that is going to be the unit of measurement. So you may want to jot that in there. So that goes for potential energy, that goes for kinetic energy, that goes for mechanical energy, that goes for any type of energy, even the energies we're going to talk about later on. All right? All right, so what is gravitational potential energy? Well, just what we did before. Gravitational potential energy technically is, I like to think of it as the energy of how high something is. So the higher an object is in the air, the more gravitational potential energy it has. All right? Also, the more mass an object has, the more gravitational potential energy it has. Why if an object has more mass, does it have more potential energy? Think about the relationship between energy and force. All right? If we were to drop a light object and a heavy object, what's the outcome going to be? Well, yeah, they're going to land at the same time. But which one's going to create a bigger divot? Heavier one, because it's got more energy. Okay, it's got more energy, it's got more force. Good. So, gravitational potential energy, just as you see in this picture, it's the potential energy due to the object's position. So, again, mass times height times gravity is going to give you the potential energy of an object. All right. So, same deal. For some reason, I find this picture funny. Deal with it. So, how can that dog have more gravitational potential energy? What two things do we have to do? Or one thing? What are two things that we have to do to that dog in order to make it have more potential energy? Push it? Why would I want to push poor old Rover? Man, well, yeah, he's got to fall first. Exactly. I guess that's the first thing. He needs to fall off that tightrope to convert it into kinetic energy. But if we wanted to increase just the potential energy, what are two things we have to do to Rover? Add more mass. Yeah. Somehow, I don't know, tape some books to him. Did someone just say beat him? Man. Or we have to hire the rope. All right? Man. So here are more examples, guys, of potential energy, just basic pictures here. So again, here's potential energy. What type of potential energy do you think this is? You guys, you ever played that game? I'm so horrible at that. And I consider myself an athletic guy, but I cannot play this stupid game. Man, what is it? I don't know what it is then if it's not an athletic game. Maybe I just need to spend more time doing it. Someone just gave me the answer anyway. Elastic. It's got elastic potential energy. So the more you stretch an elastic band, the more energy it's going to store. And then when you let that go, obviously the further you pull this apart, the more it's going to hurt when it hits you. Okay, so that's elastic potential energy. What is that picture? I totally forget why I put that picture up there. Maybe that's what it is. That's exactly what it is. Thank you, Jordan. I appreciate it. So, we have a chemical bond here. All right? The stronger the bond between them, when you break the bond, the more energy is going to be released. All right? All right, so this is what we were talking about before. Elastic potential energy. So potential energy due to compression and or expansion of an elastic object. All right, this deals with bouncing balls and also deals with that stupid paddle ball game. And again, more elastic, we're talking about stretching a rubber band. The further you stretch it, the more potential energy that's going to build up, and then when you let it go, the more kinetic energy there's going to be. So, again, guys, this is why I'm saying that this energy stuff, it's not super difficult because I think a lot of it is pretty common sense, all right? So what is chemical potential energy? What's a really good example of where chemical potential energy is stored? Batteries. Lovely. Ooh, look at that one. Yeah, it's charcoal. All right. Chemical potential energy is also stored in charcoal, because when you light charcoal, that chemical potential energy changes into what type of energy? There's thermal and light and can you hear flames? What? Do you ever sit by a fire and you hear the crackling of the fire? All right, yeah. So this chemical energy will get converted once this potential energy is used or transferred into light energy, thermal energy, sound energy. All right, so again, just showing that it's not destroyed, it changes forms. Okay? Batteries. Okay? Put batteries into anything. You put batteries into a flashlight. When you turn the flashlight on, that chemical potential energy converts into what types of energy? Light. What else? Heat. Perfect. Absolutely. And if you put your ear really close to that little light bulb, you can hear the little tungsten vibrating going. Zzz. So there's some sound energy there too. Okay? Good. So breaking it down now into kinetic energy. Here is our next formula. Kinetic energy equals 1/2 mass times velocity squared. So I'll write it just a little bit different way so you can you'll see it written just like that too. This is primarily the way that I'm going to write it. So 1/2 mv squared. Yep. So today, after our notes, you guys are going to be grabbing computers. Not done with the notes yet, but you are going to be doing something very similar to what I put up here, this picture. You're going to be messing with a little roller coaster simulation. I know Chris was all upset because you can't make your own roller coaster. I'm sorry. Yes, Jenna? Yes, any energy is joules. Great question. Any type of energy, guys, whether it's chemical energy, thermal energy, sound energy, energy is the ability to do work that is measured in joules. Okay? So down here, this is going to be an important concept to understand. You're noticing that, and you're going to notice this in your activity that we're going to do next. We have KE, we have a KE chart there, we have a PE chart here, and we have TME chart. Not time. What does KE stand for? Kinetic energy. All right? What does PE stand for? Potential energy. So notice this, guys. The amount of kinetic energy plus the amount of potential energy of this roller coaster right here. So KE, plus PE. Let me make that a little bit more. TME is total mechanical energy. All right? Mechanical energy, guys, is simply the amount of kinetic energy and potential energy that that object is exhibiting. Okay? So the amount of kinetic energy plus the amount of potential energy is going to equal the total amount of mechanical energy. Mechanical kind of meaning the energy of movement within this system. Okay? So you're going to be able to see this more when we, in about 10 minutes when we're done with these notes. So just again, when we're looking at this picture here, just notice that how these charts are changing. All right, as kinetic energy is going to decrease, we should be getting an increase. And why is there no potential energy right now? Going in a straight line. Think about the formula. All right, so think about exactly. There's no height. All right, so even if he's got a mass, sure, we know he's got a mass. If there's no height, there's no two things. There's no acceleration due to gravity. That's zero. There's no height. That's zero. And even if he weighs 25 kilograms, guess what, guys? His potential energy is zero. So that's why as he moves, guess I need to take that away. As he moves, we're going to notice that this potential energy is going down. The quicker he gets, the closer to the bottom, we notice his kinetic energy is rising. However, regardless of where he's at, whether he's up at the top or down at the bottom, if the kinetic energy rises, what happens to the potential energy? It falls. But notice that this isn't changing. The total mechanical energy is going to be the same. Okay? That's work. We haven't gotten into work yet. We're going to talk about work after we do our project. All right? So there it is. Kinetic energy equals 1/2 mv squared. That's the way I rewrote it for you guys before. So just doing a few basic math examples. I'm just going to throw these all up. So a 4 kilogram bowling ball at 10 meters per second. So we can just do the math. 0.5 times 4 kilograms times 10 squared. That's going to come out to be 200. Okay? Same thing here. 0.25 kilogram baseball. Say what? All right. We got to square it. Okay? So as we go through here, again, 0.25 times kilogram baseball at 50 meters per second, we can figure out its kinetic energy by 1/2 equals mv squared. Okay, can that be 312 joules? We will do some more math practice. Actually, today for homework, you will do some math practice. Oh, man. I heard the big sighs there. So, wrapping this up here, drawing conclusion says 2 divers of equal mass about to dive. Diver A has more potential energy than diver B. So compare the divers' positions. Who's going to have a higher position? Diver A. He's got more potential energy. If they have the same mass, we know that diver A has to be higher in the air, have a higher elevation. Okay? All right. So that was the introduction for potential and kinetic energy. Understand, quick recap. 2 main types, kinetic and potential. Potential is the energy of position. So it's the stored energy. Once that energy then starts to be unstored or unlocked, all right, it changes into kinetic energy, which is the energy of motion. All right. Now, there are 6 main types of energy, which these are going to help you understand, guys, our big project that we're going to start at the end of this week, the Rube Goldberg machines. Your Rube Goldberg machines, you are going to be responsible for doing, I forget what I think it's 10 different steps where you have to have 6 energy conversions within your Rube Goldberg machine. So you have to start it off somehow, and then through the series of chain reactions, you have to demonstrate energy conversions into other forms of energy. All right. Now these are some examples that you could do. You could do some other types as well, but these are the 6 main types. We're going to do some research where you'll be able to come up with some other energy types. But mechanical energy, like I said, mechanical energy, guys, is potential energy plus kinetic energy. So it's the energy of an object in motion. Thermal or heat energy, electromagnetic energy. That's a big fancy term. What type of energy do you think electromagnetic energy encompasses? There's lots of types. Think about if you're taking a chemistry course now, or think back to your other science courses, what the electromagnetic spectrum entails. Ghosts, huh? Light, absolutely. So visible light. Visible light, guys, so you're able to see all these colors up here because of visible light. Sure. So light energy would be in there. What other types of energy? Let me ask this. What other types of energy travel in waves? Sound? Okay. Sound, I don't think, well, sound wouldn't necessarily be in the electromagnetic, but you answered my question correctly. Sound would be a different type of energy. All right. What's that? Microwaves. Absolutely. Radio waves, X-rays, gamma rays, all right, infrared radiation. Those would all be in electromagnetic energy. Electrical energy, you guys know what that is. Plug something into the wall, that electrical energy will change into whatever type of energy that appliance is going to do. So if you plug a fan into a wall, electrical energy will then be converted into mechanical energy, wind energy, sound energy, okay? Nuclear energy. We have a lot of our energy is created by nuclear energy, and chemical energy, which we talked a little bit about today. Food is a good example of, I guess, potential chemical energy. Coal, once you light it, would be chemical energy. Good examples there. All right, I'm going to kind of cruise through these just because you have them in front of you, and I think you know a lot about this already. So what is the source of our energy? It's the sun. All of our energy, guys, that we have on Earth originates from the sun. Okay? That's why if you think about the big controversies now based on oil versus renewable energy sources, guess what, guys? Even oil is a byproduct of the sun because oil is what's going to grow the plants. Animals will then eat the plants to survive. When these animals die, after millions and millions and millions of years of them being buried and compressed, that's why they're called fossil fuels, they will create oil, which that oil can then be used for energy conversion. Okay, so all of our energy, one way or another, originates back to our sun. So here's what I was talking about before. Mechanical energy. Energy due to the object's motion or position. So the bowling ball has mechanical energy. When the ball strikes the pins, the mechanical energy is transferred to the pins. All right? And obviously, when the ball hits the pins, there's going to be a little bit of friction, so a little bit of sound will be created, a little bit of heat will be created. So all of these energy sources, guys, are transferring into one form or another. So examples of mechanical energy, so either the energy of position or the energy of movement. Basic examples of a skier, a space shuttle launching off, a swimmer, they are exhibiting mechanical energy. They are all moving, and they are all either gaining or losing elevation. I guess not the swimmer, but if it goes under the water, sure, I guess you're right. Electromagnetic energy. So light energy includes energy from gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, and radio waves. All right, that's what we just talked about. So anything within that electromagnetic spectrum. Electrical energy, again, caused by the movement of electrons, easily transported through power lines and converted into other forms of energy. This is, you guys, when I was growing up, I remember leaving lights on in my house, and one of my parents would get so mad. Oh, energy doesn't grow on trees. It's expensive. I guess it took me a little bit to realize, guys, that electrical energy just isn't created. All right? It's not like we just say, bam, there's electrical energy. How does electrical energy get created? What's that? Well, yeah, you got to turn it on. But what's going to move these electrons? So think about it. There are power plants, right? They're called power plants for a reason. There's lots of different types of power plants. There's nuclear power plants. There's coal power plants. All right? There are hydro dams, hydro dams that are going to create power. So these are awesome examples, guys, of exactly what we're talking about here. So this electrical energy, remember, it's not created. It's not just, bam, there's electrical energy. It's energy that changes forms. So when we burn coal, that chemical energy moves to thermal energy. That thermal energy is going to spin some sort of turbine, which is then going to create electrical energy. All right? Same as nuclear energy. There's stored energy within uranium. When that uranium, when fission happens, when it's going to split atoms, that's going to release energy, turn turbines, which is then going to create electricity. So, again, electricity is not simply there. It's an example of energy transformation. Okay? Chemical energy. So energy that is available for release from chemical reactions. The chemical bonds in matchsticks store energy that is transformed into thermal energy when the match is struck. Also, there's some sound energy and light energy that is created, or I should say, transferred into. So again, we looked at this before. So examples of chemical energy. We have coal or batteries. How's cotton candy an example of chemical energy? What's cotton candy made out of? Sugar. Yeah, when we break down sugar, we create energy. Okay? Good. Thermal energy. I know I'm going quickly here, but heat energy. So the heat energy of an object determines how active the atoms are. The quicker they're moving, the hotter it is. So a hot object is one whose atoms and molecules are excited and show rapid movement. A cooler object's molecules, atoms will show less movement. And finally, a recap of the law of conservation, which is what you need to do and understand in order to do the Rube Goldberg machines at the end of the week. Energy is not created or destroyed, it simply changes forms. That is the law of conservation. Okay? So any questions with the formulas of kinetic and potential energy, law of conservation, or energy types? All right, cool. We will I'm going to turn the lights on.